In the previous lecture, we have discussed the modal analysis of beams. So, performing modal analysis is nothing but solving an eigenvalue problem, as we have seen, and what we obtain the circular eigenfrequencies or the natural frequencies of the beam, and we also obtain the eigenfunctions. These eigenfunctions, they define or they describe the modes of vibration of the beam. Now, these eigenfunctions, they form a complete basis in complete basis for the shape of the beam. So, what we mean by a complete basis is something like this. So, what we mean by this, suppose we have these eigenfunctions, let us call them now. There are infinitely many eigenfunctions, as we have seen. So, here I can draw only 3, and with a little stretch of imagination you can think of this as an infinite dimensional space with each axis labeled with one eigenfunction. So, any point in this space in this space, in this infinite dimensional space with coordinates alpha 1 along w 1, alpha 2 along w 2, alpha 3 along w 3, etc. So, this describes the a shape of the beam. So, any shape of the beam may be represented as a linear combination of these eigenfunctions. Now, when we say this forms a complete basis, it means that any possible shape of the beam can be represented using these eigenfunctions. So, any possible shape can be represented in this form. Then we say that this forms a complete basis. Now, so this these eigenfunctions therefore give us a good way of representing solutions which may also be functions of time. So, suppose if these are coordinates which may be in general functions of time, in that case the motion of this point in this space may be represented through this expansion, where now these alpha k's, they are functions of time. So, they form what are known as modal coordinates. So, these and this space is known as the modal space or the configuration space. Now, this fact that any shape or any dynamical shape can be represented through this expansion allows us to solve a number of problems related to vibrations of beams, and this fact we have also seen in case of strings, and this is true in general for continuous systems. So, let us today look at two such examples. The first first we look at an initial value problem for a beam. So, the problem that we consider we have a simply supported Euler-Bernoulli beam. This beam is initially loaded with a force let us say F, at the middle. So, there is a static force at the center of the beam, which is F. So, let me write down the equations. So, when we have so the problem that we are going to address is like this, that initially this beam is deflected under the action of this constant force F applied at the center of the beam, and at time t equal to 0 this force is switched off. So, at the point this force is switched off, so the beam is going to spring back. So, the equation of motion for the dynamics problem so this is the equation of motion, and the boundary conditions So, this is the deflection is 0, this is the bending moment is 0 at x equal to 0. And same way at x equal to L. Now, the initial conditions we need to determine the initial conditions, which is the deflected shape of this beam. So, that will be obtained by solving the equation of statics So, by solving this equation along with the boundary conditions that we have here. So, if you solve this, then you will obtain and we assume that initially at time t equal to 0 the velocity of the beam is 0 and this is the shape. So, this we can substitute in here and integrate out to determine the initial shape of the beam, but we are not going to do it immediately. We are going to now first write this the solution of this problem as an expansion in terms of the eigenfunctions. We know that we can represent the solution in this form. Where these are the eigenfunctions, and for a simply supported beam, Euler-Bernoulli beam, the eigenfunctions are given by sine of j pi x over L. So, now let us first solve this statics problem at time t equal to 0. Therefore, this is going to be the equation. So, at time t equal to 0, the expansion, this expansion, so this is so C j times sine of j pi x over L. So, at time t equal to 0, this is the expansion. So, if you substitute in here, So, when we substitute this in the equation of statics, this is what we obtain. Now, from this equation we are going to solve for these Cj's, and this velocity condition will immediately tell you. So, if you consider that this is the velocity condition which is 0. So, from here substituting in the velocity condition, this is going to tell us that all these S j are 0. So, we only have these C j's non-zero. Now, to solve this, we follow the standard procedure. We multiply both sides by sin k pi x over L and integrate over the domain of the problem. So, we take inner product So, because of the orthogonality, this is going to filter out the kth term. So, if you do that, and simplify, then we obtain for odd values of k, we have C k as non-zero given by this, and for other, so for the even values of k, we have C k equal to 0. So, finally, once we have this, we can write the final solution. So, this is the final solution. of the initial value problem. So, this can be this. So, this is a function of space and time. So, one can animate this solution to determine the response of the beam. Next, let us look at another problem, which is the problem of a travelling force now. Here where we consider once again a simply supported Euler-Bernoulli beam. Carrying so, this beam is carrying a force which is travelling with a speed v. So, this problem is important in case of let us say bridges on which you have travelling loads. This is a simplified version. Here we are considering a constant force travelling on an Euler-Bernoulli beam. So, the equation of motion of this system this along with the boundary conditions and we also consider initial conditions. To be 0. So, which means that the beam is undisturbed before the force enters the span of the beam. Now, this is a forced vibration problem with a general forcing. So, we can write down the solution of this problem as the homogeneous solution plus the particular solution. Now, we already know that this homogeneous solution can be expanded in terms of the eigenfunctions and represented as in this form. this is a simply supported beam, therefore, the eigenfunctions are sin j pi x over L plus. So, this particular solution also we can expand in terms of these eigenfunctions along with these modal coordinates. So, these coordinates capture the dynamics because of the forcing. So, these coordinates will capture the dynamics of the forced motion. Now, when we substitute this solution form in the equation of motion, we so this is the homogeneous solution. So, this is going to vanish. Now, this is going to now contribute. So, this gives us so this is what we obtain, and if you simplify this by taking inner product on both sides, with sin k pi x over L, we can write this as so using the orthogonality. So, we multiply this equation with sin k pi x over L and integrate over the domain of the beam, which is from 0 to L. Now, on account of orthogonality, this taking this inner product is going to filter out the kth term in this expansion. So, on the right hand side, since we are multiplying this Dirac delta function with sin k pi x over L and integrating. So, this x gets replaced by this v t. So, then we can rewrite this now by I am dividing throughout by rho a. So, this j power 4 pi power 4 by L power 4 E I by rho a, that is nothing but square of the kth circular natural frequency of the beam. So, this is this defines the dynamics of the kth modal coordinate, and this can be written out for all the modes. So, we have the dynamics of all these modes. So, here of course, now this is a forced vibration problem for the discrete systems. Now, you see all these modal coordinates are decoupled. So, they can be solved independently, and we know the general solution of this system. So, we can easily write down the general solution of p k and construct our the solution of the beam. So, now here you can note that it is a harmonic forcing. So, the frequency of the harmonic forcing, let us name it omega, index with k. So, that is the circular frequency of the harmonic forcing. Now, there can be velocities for which this harmonic forcing equals the natural circular frequency of the kth mode. So, such a in that case we will call this forcing as a resonant forcing. So, for resonant forcing, for any k, suppose if you have this condition, and from here we know that this is so we can find out the velocity for which the kth mode is resonant. So, let me index this as also with k. So, this is the velocity which will send the kth mode into resonance. Now, for simplicity, let us first assume that this is not resonant. So, for non-resonant case, we can write the solution So, let me write the kth coordinate Now, this solution also satisfies the initial conditions for the beam, which is that it is undisturbed at t equal to 0. So, the initial shape as well as the initial velocity of the beam is 0. So, using this solution, therefore, this is our solution for the response of the beam under a force travelling at a non-resonant speed. So, which means the speeds do not take any of these values. So, if you have if the speed of travel is one of these resonant speeds, they are also called critical speeds. So, if you have a force travelling at a critical speed, in that case the solution of this gets modified, which can be easily written out, and we have studied this case in the for the string. Now, let us look at this solution at certain time instants for two speeds, one is a low speed and the other is a high speed transport over a beam. So, this this figure shows snapshots at certain time instants of a force traveling on a beam. So, you can see how the beam deflects at various time instants. Now, this is for the low speed. This figure shows the same thing when the speed is high. Now, here you can see a difference from the previous figure. From the previous figure, the deflection of the beam is completely on the negative side, below the equilibrium position. Now, here at certain time instants, there is a the beam goes above this equilibrium line. Now, let us look at these this solution through a simulation or animation. So, here the velocity is this is a low velocity that I have considered in this animation. So, you can see that the beam is always on the negative side. This black spot indicates the location of the force. The force is of course on the beam, and this is of course an exaggeration of the deflection. Now, there are two things that has to be remembered with when you see this animation. The first one is that this is a slow motion of what is happening. The second thing is that once this force leaves the beam, the response to the beam is not shown in this animation. So, this is this animation is looped, and you see only the response of the beam when the force is on the beam and traveling on it at a constant speed, which is indicated below. Now, let us see when what happens when we increase the travel speed. So, here V is L times omega 1 into pi over 4. So, this is a speed higher than the previous situation. Now, you can see that here, for example, the beam goes above. So, here beam is going above the equilibrium line. Again, this is a slow motion of what is going to happen. One more thing to notice in this solution, which is different from the previous solution, is that the deflection of the beam is much smaller in this case, since the force is traveling at a much higher speed. The beam gets less time for deflection, but this is what we observe when the force is within the span of the beam. So, you can again see the disturbance propagating forward and it is reflecting back. Okay, so, we have looked at these two examples related to application of the modal solution. Now, before we close this discussion, let us quickly look at one of the important properties of these of the eigenfunctions, which is orthogonality. So, so, we have been using this property in all our calculations, but let us now formally look at this property right from the equation of motion. So, let us consider a Rayleigh beam. So, for the Rayleigh beam, the equation of motion So, this is the equation of motion for a Rayleigh beam, and along with this of course, we have these boundary conditions. Let us say the boundary conditions so, suppose for example, we can have simply supported boundary conditions. Now, when we do modal analysis, we search for solutions of the form. So, we look for solutions of this form which is complex and separated in space and time. So, if you substitute this kind of solution in this equation of motion, we obtain so this differential equation where the prime denotes derivative with respect to x. So, this plus the boundary conditions, they complete the description of the eigenvalue problem. Now, for a moment let us write this in a compact form. Where this operator m and the operator k you can represent in this form. Now, let us write this for the jth mode So, for the jth mode it is going to satisfy this equation. For the kth mode it is going to satisfy this equation. Now, what we do? We multiply the first equation by w k, the second equation by w j, and subtract one from the other and integrate over the domain of the problem. So, if you do that and simplify, these simplification steps we have discussed also previously. So, this is what we obtain. Now, if you use the boundary conditions of the problem, suppose simply supported, then it is going to be 0 at both 0 and L, and the bending moment is also going to be 0 at 0 and L. So, these boundary terms they all vanish if you use the boundary conditions, and what you are left with and this you can see so this is the orthogonality condition for the beam. So, you see that the eigenfunctions are orthogonal with respect to this inertia operator. So, to summarize, we have today looked at some applications of the modal solution in solving initial value problem, in solving forced vibration problem, and we have also looked at the orthogonality condition of the eigenfunctions. So, with that we conclude this lecture.